Okay, so let's prove that the cut property is correct. So let's assume that we have distinct edge costs, and this is where that assumption is going to be helpful. A reminder, our cut property says that if E is the cheapest edge to cross some cut, then it must be in the minimum spanning tree. And we're going to prove this using the same technique we've used before for greedy algorithm, and that's an exchange argument contradiction. So let's suppose that E is the cheapest edge to cross a cut, but E is not part of T star. So E is not part of the minimum spanning tree. Our idea here is to do an exchange. So what should we exchange? We're going to exchange E, our edge, with another edge in T star, and the hope here is that if we can make T star even cheaper, then that would result in a contradiction and show that E belongs in the minimum spanning tree. So what can we swap with T star? Or what edge can we swap that's already in T star? So this is our picture. We have our cut, and we have that E is the cheapest edge that crosses this cut. What we want to say here is that T star must contain some other edge that crosses this cut. Otherwise, it wouldn't be a spanning tree. So we know that T star has to have some other edge that crosses this cut. So let's call this other edge F. Maybe there are other edges, but let's just point out one called F. Let's try to exchange E and F to get a cheaper spanning tree. So let me ask you a question and give you some options here. If I take T star, which is a set of edges, and I add to it E, so I'm going to do a set union, and then I subtract out of it F, will I still have a spanning tree of our entire graph? Okay, so let me show you a more specific graph. So let's say that we have our items that have already been found by prims and the items that haven't already been found by prims. And here's our cut. And we have some edge F, we have another edge E, and some other edge G. We could have more other edges, but this is enough for the example and to answer this question. Well, if we swap E and F, do we still have a spanning tree? Well, no, in fact. So what I had before was all of these vertices, and they could get to all of these vertices, and through that they could still get to all these vertices. But if I subtract F and add E to this, you'll notice that these are now sort of disconnected over here. So the answer to this is, well, sometimes yes, sometimes no, which means the real answer here is maybe. This is just misdirection. So how do we know if the edge we're swapping with is the correct edge? So, you could have any number of edges that cross this cut. Which one do I swap E with? Well, our hope here is that we can always find some suitable edge E prime that, with an exchange, we always end up with a valid spanning tree. All right, so here I've got sort of a messy looking graph, but what we have here is a set of vertices, and the green lines belong to T star. So the green lines belong to T star, and these rainbow edges are just other edges that exist in the graph. And for that reason, we can just sort of ignore those for now, because we're not going to do a swap with E with one of those rainbow edges. They're not even in the graph. All right, so this is the spanning tree we have, and we've removed and pruned out the other edges. What happens when we add our edge E? Well, when we add our edge E, that's going to be sort of n edges when we have n vertices, which means we're guaranteed to have some form of cycle. So it's going to create a cycle. And just as a reminder, a tree is always going to have n-1 edges, and now we have n edges. So we're going to create a cycle. And the nice thing about that is the cycle has to cross the cut. E has to be part of the cycle. So which edge can we exchange with E? We have to exchange one of the other edges that's part of the cycle. So here's our cycle, and there's another edge that crosses this cut. So we're going to say C is the cycle that we created by adding our edge E. And we're going to find all edges that cross that cut. And by the double crossing lemma, we know that there must be some edge E prime that crosses the cut. So E prime is the other edge that's part of the cycle that crosses the cut. So now if we take T star and we add to it E and subtract out E prime, do we still have a spanning tree? So that's our exchange. And since they were part of a cycle, we're guaranteed to still have a spanning tree. Well, what happened when we did this? Well, we said that E was the cheapest edge to cross the cut. So when we do this exchange, we end up with a spanning tree. And since the cost of E is less than the cost of E prime, our new spanning tree is cheaper than T star. So we've now refuted the previous optimality of T star, and we've shown that when you add this cheapest edge that's crossing a cut, that's going to give you the optimal spanning tree. All right, so now we've proved that it's a spanning tree, we've proved that it's a minimum spanning tree, and we've proved our last little point here, which is that the cut property needs to be correct. All right, so one last thing we haven't spoken about is the running time of Prim's algorithm. So we have big O of n for the outer loop, and, well, it could take as bad as big O of m to search through all of the edges that cross this cut. But can we do better than big O of m times n? And the answer is that we can easily get this to big O of m log n the same way that we did for Dijkstra's, which is to put all of our vertices into a heap and mark their keys as the cheapest edge that connects them to an edge that's already in the found set. We'll talk more about the running time of these minimum spanning tree algorithms when we get to Kruskal's algorithm, which is in the next set of videos.